So now let us continue with the distinguishing test for alcohols as well as phenols. So when we consider phenols can turn phenols can turn blue litmus. Phenols can turn blue litmus to red litmus. So it can easily turn blue litmus paper to red litmus paper, and it can also react with aqueous alkali. It can also react with aqueous alkali to form an phenoxide ion. It can also react with aqueous alkali to form a phenoxide ion, or it can also form phenates. So when I consider with this, when I write the structure of a phenol, when it is made to react with NaOH, we know that phenols are highly acidic, which can form an ion called as phenate ion or phenoxide ion along with the elimination of proton, and this NaOH ionizes as Na plus as well as OH minus. This C6H5O minus will combine with what? Na plus, so that I can write it as C6H5O minus along with Na plus, which is considered as sodium phenate, or you can also write it as sodium phenoxide along with the elimination of water molecule. But when I consider an alcohol does not react, or alcohol neither turn blue litmus. Alcohol neither turn blue litmus to red. Alcohols neither turn blue litmus to red, and it will not react with aqueous NaOH solution. Means when we write the reaction of an alcohol with aqueous NaOH solution, there will be no reaction of an alcohol with aqueous NaOH solution. So by this we can explain the acidic strength comparison with reference to alcohol as well as phenols. So what are the major explanations that has to be known in the comparison of acidic strength of alcohol as well as acidic strength of phenol? Let us analyze. So here R is considered as an alkyl group, where this alkyl group is electron donating in its nature, or I can also call it as electron releasing group. But when it comes to phenol, in phenol there is an aromatic ring, that is benzene ring. This benzene ring is electron withdrawing in its nature. So when I compare both alcohol as well as a phenol, in alcohol, alkyl group donates extra electron towards oxygen, whereas in phenol, the benzene ring withdraws the electron density towards itself. So in phenol, as the benzene ring withdraws electron density towards itself, hence, so I'll write it as, in phenol, the benzene ring withdraws electron density, which decreases the electron density on oxygen atom. So here, as the benzene ring in phenol, as the benzene ring withdraw electron density, which decreases the electron density, as benzene ring withdraw electrons, which decreases the electron density on oxygen atom of which group? It is OH group. So by this we can clearly analyze that the oxygen atom tends to pull. So in this phenol, when I consider it as OH, the oxygen has two sets of lone pair of electrons present in it. So these electrons can be involved in what? Cyclic delocalization of electron. So as a result of this, oxygen atom tends to pull the shared pair. Oxygen atom tends to pull the shared pair of electron towards itself. So when the shared pair of electrons are pulled towards itself, it increases the polarity. It increases the polarity of the OH bond in phenols. So if the polarity of OH bond in phenols goes on increases, these phenols are called as stronger acids. These phenols are called as stronger acids than alcohols. Now a question arises, how oxygen withdraws the electron density towards itself? Here this can be explained by considering the phenol. Phenol may be considered to be a resonance. Phenol may be considered to be a resonance hybrid of following structures. So when I write the resonating structures of phenol, we can clearly understand that. So this is the structure of phenol, where oxygen contains two sets of lone pair of electrons present on it. When one set of lone pair migrates here, these electron shifts here, so that I can write it as this position becomes electron rich with a double bond with O and H, a positive sign on oxygen, and one set of lone pair. Again these electron shifts inside the benzene ring. These electron will shift at this position. Hence I can write it as this will be negatively charged with a double bond OH with one set of lone pair along with a positive charge. When these electron shifts here, these electron will shift here, so that I can write it as, so this will be a negatively charged, along with that a double bond of OH with a positive sign and one set of lone pair. If these electron shifts here, again the electrons are given back, so that I can write the resonance structure of what? Resonance structure of phenol again. So by this we can clearly understand that due to the presence of this oxygen atom, this oxygen atom pulls the shared pair of electrons towards itself, because these electrons are in link with what? Carbon. If these electrons are involved in cyclic delocalization, this increases the polarity. So here you can observe polarity of negative sign and positive sign in phenol. Therefore I have mentioned here, as a result of oxygen atom which tends to pull the electron pair or shared pair of electron towards itself, this increases the polarity of OH bond. See here, you can notice the polarity in OH bond which has shown a positive sign along with the existence of a negative sign. Therefore the increase in the polarity of OH bond in phenols. Therefore phenols are called as an stronger acids than alcohols. So such kind of resonance structures is not possible with reference to phenol. So based upon this, we can further tell that as a result of resonance, oxygen atom acquires which charge? A partial positive charge. This weakens the OH bond and facilitates the release of proton. So here further I can explain it as, so since we have written the resonance structures, I can write it as a result of resonance. As a result of resonance, oxygen atom has acquired a positive charge. As a result of resonance, oxygen atom has acquired a positive charge. This weakens the OH bond. This weakens the OH bond and thus facilitates the release of proton, that is H plus. So this can be shown by a chemical reaction of, so this is the structure with relevance to phenol. So this phenol, upon reaction with water, where oxygen has two sets of lone pair associated with it, so this hydrogen gets eliminated as a proton, so that I can get which ion? A phenate ion or a phenoxide ion. Along with this phenoxide ion, there is a formation of hydronium ion. This is called as phenoxide ion. Further, we can clearly mention the canonical structures or the resonance structures of these phenate ion, so that the phenol which is obtained, so this is the structure of phenol. So this phenol can readily give which type of an ion? It can readily give a phenate ion along with a proton. And this phenate ion, which has a negative charge present on it, it undergoes cyclic delocalization of electron. Thus, the resonance structures of phenol have charge separation. Due to this, the phenol is considered as unstable as compared to phenate ion, because the phenate ion has a negative charge present on it, and hence this negative charge undergoes delocalization and it is stabilized due to resonance. The phenate ion is stabilized. The phenate ion is stabilized due to resonance, and the structures of phenate ion, the structure of phenate ion resonance is as shown below. So when we write the resonating structures of phenate ions, the resonating structure of phenate ion can be mentioned as, so this is O minus, this electron will shift here, again these electron will undergo a migration, where I can write it as what? A double bond O with a negative charge at this end. Again this negative charge shifts, these electron will be shifted here, so that I can write it as what? A bond here with a negative charge at para position along with a double bond O. If these electron shifts inside the benzene ring, these electron will shift here, so that this structure can be represented as what? At the ortho position, again in negative charge with oxygen. If this electron shifts here, again the migration of electron takes place on oxygen, which is represented as, again it gives rise to a phenate ion, so that the negative charge which is present on the phenate ion undergoes cyclic delocalization, so the phenate ion is stabilized due to resonance. And these are the different canonical structures of phenate ion. By this, we can clearly understand that the phenate ion is stabilized by resonance, and the phenol is unstable as compared to that of an phenate ion, which is explained by the resonance structures, which is as shown below. Thank you.